is Lorraine Prokop of, she will be giving us a talk on Orion Optical Navigation. She's with NASA LARC.
Hi, I'm Lorraine Prokop, as he said, and I'm going to do a project overview and lessons learned from a project called Orion Optical Navigation. Next page. I was the software lead for this, for the release that's going to fly on the Artemis 1 mission, currently scheduled for November of this year. I have since then taken a new role with the NASA Engineering and Safety Center, the NESC. And I guess I'll just take a moment to plug the fact that I did do a pre-recorded video to talk a little bit about what the NESC does and what the Tech Fellows do. So I'm the Software Tech Fellow. Many of you might have known Mike Aguilar. I succeeded him in that role. But anyway, there's going to be a YouTube video, 15-minute on that, posted at some point later. But succeeding me as the lead, I wanted to introduce you to another couple of folks who Mike Buttacoli on the right has taken the reins on this project and has been leading it for the Artemis 2 and beyond. And really the spearhead of the whole project, the project lead, is Dr. Greg Holt. They're both out of JSC. So feel free to contact any of us after this pitch if there's any further questions. Next page, please. So what is optical navigation? Oh, I see that in my video, the lower left picture doesn't look so good, but this is a fixed mounted commercial camera that's mounted underneath the capsule in between two star trackers. Again, it's fixed mounted. You can see a picture of it on the right. It's a still image camera, but it processes these still images for autonomous spacecraft navigation. So the onboard Orion spacecraft and all historic spacecraft have typically gotten navigation state updates from the ground. But if the communications with the ground is lost, you could lose the spacecraft if you don't have some other means of getting these trajectory course maneuver updates. So what this does is it serves as a backup for a comm loss to complete the mission to the moon and back. So this instrument and the software together, they compute an onboarded nav solution to substitute for nav data that would traditionally be provided by the ground. Next. So this is just kind of a cartoon starting on the upper left. Assume you're going to the moon and want to return to Earth, and you lose comm. So what this system will do, and you can see these red lines on the chart, these are dedicated times in the Artemis 1 mission where the vehicle would be taking autonomous navigation measurements, slew the vehicle to look at either the Earth or the moon, and to take measurements to support burn targeting. So towards the moon, around the moon, and then all the way back till the final burn target for the entry, re-entry. So the performance requirements on this instrument were really to be able to complete that mission with the accuracy enough to hit the entry corridor, which is fairly narrow. So, okay, next chart. So this is the upper left is just another visual of when these dedicated, what they call OpNAV passes, will happen during the mission. So the center, the green dot is the Earth, the blue dots is the moon going around the Earth during the roughly three-week mission, and the red would be is the outbound leg of the mission, and the pink is the inbound leg of the mission. And these are when this instrument is activated for the readings so that it can provide the burn targeting updates. And during these passes, images are taken every 30 seconds. And you know, one of the interesting things is, in order to do this, because it's the fixed mounted camera, the vehicle is slewed to point to either the Earth or the Moon to take these still images. Next. So this just gives you kind of an architectural picture of it. The software itself is an OpNAV app that runs in a camera controller computer, and this is external to the primary flight computers. It's a 64-bit Linux box running a CFS, and it communicates to the optical camera with a USB, and then it communicates over the Orion internal networks between itself and the primary GNC, the vehicle computer that has the GNC apps on it. So there is bidirectional communication. The GNC app actually commands when to take a picture, and it also adjusts closed loop exposure and gain settings. So there is a little bit of a closed loop, but then the final results is the data returned to the GNC to go into the navigation filter. And for Artemis 2, the data is going to be a crewed mission. The data will go to a crew display, and there also is comm with the ground. But of course, it was built to work when in the absence of comm. So that the ground intervention there is really just for monitoring during its first mission. Next chart. So some basics of the software. Still images of the Moon or the Earth are processed to find the apparent angular diameter and a centroid in the camera plane. You can see the kind of the image on the right. It's, you know, it's tracing this arc, and then if you know the size of the Earth or the Moon, you can tell how far away you are, and it also determines the centroid of the body. So this raw data is transformed into range and bearing, and it also uses a star tracker bootstrap, but it self-corrects for slight star tracker misalignments. So for Artemis 1, it primarily does range and bearing, and it receives star tracker attitude. For Artemis 2, there's a progression to do attitude determination, basically act as another star tracker. And for Artemis 3, I think the plan was to add targeting to gateway for autonomous rendezvous. So measurements are sent to the GNC, the Kalman filter, to update the onboard state vector. One of the interesting things that this app does is it calibrates itself and undistorts images in real time based on star image centroids. So there's special times where prior to each one of these passes, the camera is pointed not to the Earth or the Moon, but to the star field. And it will use the star field to characterize any lens distortion or do tweaks to the attitude from the star trackers. So this was being put into Artemis as a mitigation for the loss of comm. So it is a safety critical feature, because that would be loss of crew or loss of vehicle if you lose comm and you can't get these state updates. So it was developed as a Class A safety critical, and under the CMMI level 3. For Artemis 1, it was about an 18-month development effort. Just to note, I have a picture there of the Apollo space sextant. So getting an onboard navigation update isn't new. The way it was done for Apollo was a manual sighting, to confirm and or if you lose comm to come up with bearing and range. So this is sort of an autonomous analogy or replacement for that. Next. So this is a single CFS app. I have to put up the bubble chart. It runs under the Core Flight System framework and gets images off the file system. The camera drivers are non-CFS apps that run outside of the framework, so there's special apps that communicate with those, and then the data is shipped over to specially adapted telemetry input and telemetry output and command ingest apps that were written for the Orion spacecraft. Yeah, it runs at 1 hertz. Yeah, that's all I wanted to say on this chart. Next chart. So this kind of goes into a little more detail of the design of this app. It is broken into several CCSIs. The main one that has interface to the external world is called the CFS app. This is the one that does all the I/O to and from the software bus and orchestrates the situation based on commands that it gets. The image proc is the main app that does the range and bearing based on looking at the planetary bodies, the Earth or the Moon. The image cal is the thing that does calibration and undistortion, the lens undistortion. And there's the bottom one, image app, that's a later for Artemis 2 added for the attitude determination. And then there's some common functions that everybody uses. Next. There was quite an extensive test campaign done on this software because we had strict requirements for performance, but also we had this driving need to not have false positives. So, and because it was safety critical. So just trying to give you maybe a pictorial representation of the test framework that we had. We did unit tests with UT Assert with full coverage, MCC permutation testing, and then we did code inspections. We did static code analysis. You can see the tools listed there. And we did verification tests, but one of the things we did was we wrote this Python test framework to orchestrate all these tests with thousands of nominal images as well as off-nominal images, and that this was all run in nightly regressions and continuous integration type of fashion. Next. So again, to just summarize the test campaign and some of the statistics on this, some of the key performance requirements I mentioned were the accuracies needed to do the targeting. And the other thing is we'd rather have it fail than to put output data that was out of its own spec. So it's better to not provide output than provide output out of tolerance. So you could count on the accuracy of the data. And then the test campaign, this followed a waterfall development life cycle. And so we had all the major reviews and did the unit testing, code inspection, static analysis. And then we verified with synthetic images because although there are images of the Earth and Moon, we couldn't get those paired with time with enough accuracy. So we tested with some images of the Earth and Moon, but not for our verification because we needed accurate time for that. So we did synthetic imagery for that. And there were an extensive set of nominal and off-nominal test cases. And then we did robustness testing to see how say, far away from the moon can you get before it fails? So we would characterize the performance of this. We did integration testing in higher and higher facilities. And then one interesting thing about this is that it's not really yet validated. The plan for this software is it will be validated on the outbound leg to the moon during the mission, and then used on the inbound leg, activated for the loss of comm case. So it's about 8,800 lines of C flight software. And an interesting metric is that the test software was 35,000 lines of code. It was about 4 times as much. And we had 21,000 individual pass-fail test cases. And you can see 3,300 nominal images and 2,200 off-nominal images. So we ran a lot of images through these tests. Next. This is just a screenshot of showing what happens if you looked at the GUI to control the test framework for the individual verification tests. And it's just interesting because you could watch this run, and you wanted the screen to be all green, let's put it that way. So next page. And one of the things that we employed that was kind of a new process that worked really well is we had these things called incremental verification test reviews. So every time a developer or tester got a verification test complete, we would have a peer review with it. So you see here, this is just a collection of the tests after they were successfully peer reviewed. So you could have, like, each one of these tests had its own kind of mini design review. Next. So this is kind of a chart just throwing together a bunch of sample images that we used in this. On the upper left are sort of the nominal images that were generated based on the expected launch date and what we thought that the camera would actually see. And it's interesting when you look at the range. On the leftmost one is a large Earth, and that dim one that you can hardly see is a dimly lit crescent moon. So the camera had to perform within the accuracy for that range of images, and it did. And then, of course, we had to take into account that there may be all different exposures. You might not be exposed correctly. So we had to test with that. And then I have to hand it to the team, very ingenious, trying to think of ways of breaking this software. We came up with lots of off-nominal conditions. The upper right is the Earth and Moon in the image, and it could navigate with that, even just telling it, well, use the Earth or use the Moon. It can tell the difference between these two. And just things where there wasn't any limbs in the image. There's debris, sun flares, lens scratches, solar panel in the way, all kinds of things like that we tried to throw at it. Next page. So just some of the lessons learned that I captured during the course of this development. The team initially started with using MATLAB Simulink to autocode, and they quickly went to hand code for this, for optimization, readability, and to better control off-nominal conditions and failure scenarios. And this was a team of people that were not necessarily familiar with C, but were familiar with MATLAB. But it wasn't really a big deal to do the learning curve, and they adapted really quickly to that. We didn't initially use Doxygen to link the code to the design, but we should have, and that was corrected in the future releases. We also, I choose not to use one of my own previous products, the CFS Command and Data Dictionary. Chose not to do it, thinking this project was too small, but was sorry we didn't do that, because maintaining your data dictionary by hand was not so good. And then I mentioned that we did these incremental verification test reviews, which is a really valuable process addition that we did. So when we had these verification tests, we were confident that we had they'd been peer reviewed, they were tested right, tested enough, and we actually had very useful code inspections. And I've found that this is sort of a hit or miss. Sometimes code inspections are not that valuable, but in this case, if the right people were there, and they were very valuable. And in fact, they were way more valuable than the static analysis, because what we found in the static analysis is it couldn't detect things that were missing from the code. I mean, the static analysis runs over the code that you have, but it doesn't point out holes in the code. And that's what the people were really found. And then we should have allowed more schedule. We didn't really have that luxury because this crossed a lot of TRLs in very short time. And then yet again, testing was under scoped. I think we planned for 2 times the code, and it was 4 times. But if we would have had a test framework to start with, I think things would have went better. But I think that's in work too. Next. So this is going to be the first autonomous safety critical onboard nav system in the Earth-Moon system. It was developed for the Artemis missions. Artemis 1 is going to be validated hopefully in November by doing range and bearing. And it is out there on software.nasa.gov, available as US release, I believe, because it was developed as GFE. I think that's all I have. Let's make sure. One more, yeah. Any questions?
Yeah, thanks, Lorraine. We do have a few questions. First question from Gabriel. How were the synthetic images for testing created? If they are created by an algorithm, isn't there a risk of creating biased images and not handling corner cases?
Yeah, well, there was a lot of work. We used a tool called Edge that was originally developed at Johnson Space Center to help with astronaut training. And we, over time, adapted it to produce images that were of the fidelity that we needed, and we validated that against other pieces of software and other images that we knew to be truth. So we validated our own tools and had to put in quite a bit of work to make things as accurate in that generation as we needed.
All right, great. Next question is from Dimitri Becker. You mentioned 64-bit Linux and USB, and these are things that are not usually seen in deep space missions. What kinds of processing hardware are you using, and are there radiation fault tolerance concerns? Are these COTS or in-house design processors?
Yeah, so this is a little bit of a risk on this project. The processor that it's in is a PowerPC commercial computer, and and the camera for that matter is also commercial. They're both tested to be rad tolerant to a certain degree, so we have. Yeah, it's a little bit of a risk, and if they start relying on this more, I think the plan was to rehouse it in a more, flight qualified, rad tolerant, rad hard processor. So yeah, you're right. That's one of the big risks. We have flight critical code in a rad soft processor for Artemis 1, but the plan is, like I said, to evolve this into something more rad hard.
Okay, I think related to that, we have another question from Brandon Haber, our technical chair, and he was wondering. He said that you said it was Class A safety critical software and also running a Linux OS. Are there any problems with that combination?
Yeah, well, that was another one. yeah, we as I said, we try to maybe evolve to something more traditional for the safety related software, but we basically accepted the risk for now. The other thing is this processor, the measurements aren't that there aren't tight deadlines, right? So if we can produce a measurement every 30 seconds, so it isn't like that it has really high, real time critical or tight deadlines, and we just accepted that risk.
All right, great. So there are still a number of questions. It's 3:05, time for our next activity. So what we'll do is we'll copy all of these questions over to the Talks Slack channel, and then they can all get resolved over there. Thank you very much, Lorraine, for an excellent presentation.